Dear ladies and gentlemen, my name is Lucie Malikova, and I would like to introduce you our work that is devoted to investigations on influence of biomaterial interface on the crack propagation through a thin protective layer. We have worked on this topic together with my colleagues Petr, Miarka, Pavel, Doubek, and Stanislav Seitl, and our team works both for Brno University of Technology and for Czech Academy of Sciences. Our presentation has got the following parts: introduction and motivation, few words about the laser cladding principle, aims of the work, geometry and numerical model, then the most important part about the results and from them resultant conclusions, and finally several suggestions and ongoing work. So let's start with a short introduction. In industries such as automotive, aerospace, petrochemistry, and so on, there are many components of various machines exposed to, for instance, high mechanical stress and or chemical effects or high temperatures. Thus, it leads to reduction of lifetime of such components, which is, of course, unwanted. Laser cladding is widely usable in machine parts, repairing, and functional coatings because of its main advantages. Many variants of functional layers can be applied, lower dilution rate, small heat-affected zone, and good metallurgical bonding between coating and substrate. The basic principle of laser cladding can be seen in the figure where the metal powder or wire is fed to a laser beam, where this material is melted together with the base material of the part, and a deposition layer is formed on the surface of the part. The main aim of the work presented is to study crack behavior in a surface layer cladded on a base material. Several combinations of layer substrate material properties are considered. As the material of the substrate, two kinds of steel are considered: a tool steel and a structural steel, with the presented elastic properties, Young's modulus and Poisson ratio. As the materials of the surface layer, the following material can be used: hard chrome, two kinds of aluminium bronze, high strength copper beryllium alloy, and a cobalt alloy. And also you can see the elastic properties again. So, with regard to the real structures, the following geometry was chosen for numerical simulations. The outer radius of the component is between 80 and 90 millimeters, where the substrate represents the massive part of the component and a thin layer or two are cladded on its surface. After laser cladding, machining of the surface is necessary, and sometimes also annealing. A numerical model was created as a simplified bimaterial cracked bar under pure tension in the first step of the research. Here you can see the schema with the particular dimensions in the figure and in the table. Whereas the elastic modulus of the substrate was kept constant as 200 gigapascals, the elastic modulus of the surface layer was varied from 100 to 300 gigapascals. Also, the influence of the thickness of the layer was investigated. and the values of 1, 2, and 3 millimeters were considered. The crack was modeled from a very short to very long in the surface layer. In the finite element software, quadrilateral 8-node elements were applied. They are called plane 183 in ANSYS. Of course, a refined mesh considering the stress singularity at the crack tip was created and plane strain conditions were applied. The material was subjected to pure tension of 800 megapascals. Here you can see the finite element mesh, first in the whole specimen on the left and then near the crack tip on the right side here. Now this figure shows already the results of the pilot numerical simulations, particularly the dependence of the stress intensity factor on the crack length for different values of the modulus of elasticity of the layer material can be seen. Note that the gray curve represents the case of the homogeneous material because the Young's moduli of both materials have the same value. It means 200 gigapascals. This result corresponds to the 1 millimeter thin surface layer. These horizontal black lines represent the common values of the threshold stress intensity factor, this 8 megapascals square meter, and its critical value, 60 megapascals square meters. Analogical results were obtained also for the thickness of the cladded layer of 2 millimeters and also 3 millimeters. So you can see how the curves are moving in the same scale. When the results are mutually compared and analyzed, the following discussion can be made. Higher Young's modulus values of the protective layer in comparison to the Young's modulus of the substrate make the fatigue crack propagation easier or faster, let's say. All of the materials considered as the protective layer, hard chrome, aluminum, bronze, high-strength copper barium alloy, or cobalt alloy, are therefore more compliant than the construction or tool steel, or at least as compliant as the steel. Note that for the following discussion of the results, common values of the threshold stress intensity factor delta K1TH and critical value delta K1C are considered. The presented discussion can be then modified for arbitrary values of these material parameters. Thus, considering the threshold stress intensity factor of 9 megapascal square meters, a crack of the length of 0.03 millimeters will not propagate in a homogeneous steel at all. The more compliant is the protective layer, the longer some surface defect can be presented without starting to propagate. For example, if the Young's modulus of the layer is 100 gigapascals, then the threshold crack length is equal to 0.13 millimeters. Moreover, a higher protective layer thickness increases slightly the stress intensity factor values for the same crack length. It means that it makes the crack propagation easier or faster, let's say. Considering the critical value of 60 megapascals square meters, the unstable crack growth occurs when the critical length of the crack is equal to 1.4 millimeters, when only the substrate material is considered. The compliant surface layer then increases the critical length necessary for unstable crack growth. For instance, if the layer has the thickness of 3 mm and Young's modulus of 160 gigapascals, the critical length of the crack is equal to 2.5 millimeters. Of course, for lower Young's modulus, AC is even higher. Thus, more general conclusions can be stated. Protective layers from more compliant materials than the substrate material can be clearly recommended from the point of view of fatigue crack propagation. The compliant surface layer increases both the threshold crack length, ATH, necessary for starting the fatigue crack propagation, and the critical crack length, AC, necessary for unstable crack growth. The choice of the suitable thickness of the protective layers can be done only when additional analyses are performed, because so far a clear conclusion cannot be stated from the results presented. At the end of the presentation, the following suggestions on the future work can be made. The results presented are a part of the project Influence of the Bimaterial Interface on Initiation and Propagation of a Short Fatigue Crack, which started 2 months ago. These pilot results are going to be complemented by lots of additional studies, such as other types of loading can be applied, or the behavior of a crack with its tip directly at the bimaterial interface can be investigated. Crack entering the substrate material can be modeled, and its behavior can be investigated with regard to the elastic properties of both materials, protective layer and substrate, and so on. The project should bring recommendations on the proper material of the surface layer, as well as on the choice of its optimal thickness to ensure as high fatigue life of the component as possible. At the end, I would like to acknowledge the financial support from the Faculty of Civil Engineering, Brno University of Technology, and of course, I also thank for your attention.